In this video, we're going to continue with some examples of concavity and curve sketching, and we're going to focus on a rational function that also includes an exponential. Let's consider the function y equals e to the x over x. So if we look at our asymptotes, like we've done before with our rational expressions, again, our vertical asymptote is found by what makes our denominator 0, but wouldn't cause a removable discontinuity, which would be x equals 0. Then to find our horizontal asymptote, we do our limit. Now, as it turns out, this is actually a very easy limit to evaluate using the material in the next section on L'Hopital's rule. But we're going to just kind of consider what's going to happen as x approaches infinity here. Well, as x approaches infinity, e to the x is going to approach infinity, and my denominator is also going to approach infinity. But let's think about this for a moment. E to the x is going to grow much faster than y equals x. So the numerator of this is going to overtake the denominator, and so what happens is this is going to approach infinity. Well, when that happens, then we have no horizontal asymptote. So in this example, we have no horizontal asymptote. So now we're going to go ahead and work with our derivative. So if I find f prime of x, then by taking the derivative, we have a rational expression, so we're going to have to use our quotient rule. We would have the bottom times the derivative of the top minus the top times the derivative of the bottom over the denominator squared. Well, that is x e to the x minus e to the x over x squared. But notice that in the numerator we can factor out an e to the x. So let's do that. And when I do, this is the problem that I'm going to come up with. So I need to know what makes this problem or this function equal to 0 or be undefined. Well, undefined is going to happen when x equals 0. So that's going to be one of my critical points. When the numerator is 0, then the fraction itself would be 0. But e to the x as a function is never 0. It's always some positive value. So really all I need to know is what would make x minus 1 equal 0, which would be 1. So my two critical points on this would be 0 and 1. And now we're going to make our sign chart. So let's pick some values, and we'll use -1, we'll use 1/2, and then we'll use 2. Now we're going to look at our function, and I'm going to again look at my factored form of this and substitute into there. Well, I can save myself some time by noticing what's happening. X squared on the bottom is always going to be positive no matter what value I substitute in. E to the x on the top is always going to be positive. E to any power is always a positive answer. So really all I have to focus on is the x minus 1. So if I put in -1, -1 minus 1 would be a negative number, and everything else in that problem was positive, so I'm going to have a negative value. If I use 1/2 for my value between 0 and 1, again, if I put 1/2 into just the x minus 1, I would have a negative number. Everything else was positive, so that answer is negative. And then if I put in 2, 2 minus 1 would be 1, which is positive, and everything else in that problem was positive, so that would be positive. So now I have when I'm increasing and decreasing, so I can write all of that up. So this problem would be increasing from 1 to infinity, and it would be decreasing in two different places. Now remember, we have to exclude 0, so because it was excluded from our domain of my original problem. So it's decreasing from -infinity to 0, and then union from 0 to infinity. Now one of the things I do need to consider is, could this point here, where I change from a negative to a positive, be a relative max or min? Well, look back at my original function. I do have a change in sign, and my function is defined at x equals 1. E to the 1 over 1 has a value, so I do have since that would have been decreasing then increasing, I do have a relative mean there. So if I put 1 in to my original problem, I'm going to get e to the 1, which is e over 1, but e over 1 is just e. So we do have a relative mean at 1e. Now let's work with our second derivative. So I went ahead and rewrote this problem for my first derivative back in the unfactored form, so I could just take my derivative in that form. So my second derivative would be my denominator, x squared, times the derivative of my numerator. Well, the derivative of x e to the x, you're going to have to use the product rule, would be first term, derivative of the second, plus second term, derivative of the first, then minus, let's not close that yet, the derivative of e to the x, which is e to the x. So that's denominator multiplied by derivative of the numerator, minus, and now we keep the numerator and multiply by the derivative of the denominator. And all of that is over x squared squared. Now, first thing we want to notice is right inside of my parentheses, notice that I have a positive e to the x and a negative e to the x. So those are going to cancel, and that's going to make this a little easier to work with. So I have my second derivative is going to be, using distributive property here, x cubed e to the x. Then I'm going to distribute the 2x and my negative. So let's make that plus, and then we'll make that negative 2x and distribute a negative 2x. Negative 2x squared e to the x plus 2x e to the x all over x to the fourth. Well, now I notice that I can actually factor out an x and an e to the x in the numerator, because every term in the top has an e to the x and has an x in common, and that would give me x squared minus 2x plus 2 over x to the fourth. Then I could cancel out an x in the numerator with one of the x's in the bottom. So here's what I have right now for my second derivative. So I have e to the x times the quantity x squared minus 2x plus 2 over x cubed. Now we need to get our critical points. So what would make our numerator 0 and our denominator 0? Well, the numerator would be equal to 0 if x squared minus 2x plus 2 could be equal to 0. We've already discussed that e to the x can't be 0. But if I look at x squared minus 2x plus 2, that doesn't factor, so I might try quadratic formula, and what you'll see is from the discriminant that that's going to have imaginary roots. So we can ignore that part, and let's just see what makes the denominator 0, which would be at x equals 0. So 0 is going to be my only point that I'm going to use for my second derivative sign chart. So let's pick points on either side of 0. So we'll use -1 and 1. So if I put -1 in, and again, let's kind of see what's happening here, that we know is going to be positive. So we really just need to focus on these two parts of the problem. So if I put -1 in on the numerator, I'm going to have -1 squared, which would be +1, minus 2 times -1, which would be +2, and then +2 more. So we have a positive on the numerator, but a negative in the denominator, because -1 cubed would be negative. So that answer is negative. Then if I pick a number bigger than 0, like 1, I'm going to have 1, looking at the x squared minus 2x plus 2, I'd have 1 minus 2 plus 2, so that's positive, over the denominator, 1 cubed is positive, so that's positive. So there's my sign chart. All right, so let's take everything that we have now and put it together in a graph. I did go ahead and put my concavity from my sign chart. We had that it was concave down from -∞ to 0. and that we would be concave up from 0 to infinity. I do want to just point out quickly why I didn't list a point of inflection, because we do have a change in concavity, but remember from my original function, we had e to the x over x. 0 is undefined, or 0 is going to make my equation undefined, so it's left out of my domain, so that's why we don't have a point of inflection there. So we do have a vertical asymptote at x equals 0. So the y-axis is going to act as a vertical asymptote. So let's sketch that in. So we want to have an imaginary line along the y-axis. And now let's plot what we know. We have a relative min at 1e, so 1 and almost up here at 3, so at 2.7. So we'll try to sketch that in there. And now, all we know is that our graph up through 0, so let's look at that, is decreasing from our first derivative, and it's concave down. So if we are decreasing and concave down, since we have no points on the left-hand side of this graph, let's pick a point to substitute in and at least get some idea of where we might sketch this in. So if I put -1 into my original problem, I don't really need to know what the answer is, although it would be e to the -1 over -1. I do know this, it's negative. And as a matter of fact, no matter what value of x I substitute in to my equation, my original equation, everything less than 0 is going to give me a negative value. So remembering that we were decreasing and we were concave down, and we had to have negative values all the time, that's going to sketch in something that looks like this. Now, from 0 to 1, we're still decreasing, but we've changed to concave up. So using this as our asymptote, we know that we're going to be coming in like this, decreasing and concave up. And then from 1 on, our graph goes back to increasing and concave up. So I might expect it to look something like that. And that should resemble what our graph will look like. And again, you can always go back and check that with your graphing calculator. Notice that this problem required a lot more work algebraically when I took the derivative and the second derivative. So that's going to be especially the case when you work with rational functions. Many times the derivatives can get a lot more complicated just to find your critical points so that you can plot.